Hi everyone, this is the Pitt AWM Student Seminar Series. Our next speaker is Yixuan Wang from University of Pittsburgh. Yixuan, you can continue.
Yeah, I will share my screen now and okay, so today the topic for my research is a strong solution for the compressible liquid crystal system with a random force. And this is a joint work with Zhao Qiu. So at first, I'm going to introduce the nematic liquid crystal model. So this is for the deterministic model one. So the liquid crystal are the classical examples of metal phases that are intermediate between solid and liquids. You can see the model is like this. And here in rho, we denote as the density. And this U is the flow velocity. Q is the nematic tensor order parameter. And Q is the 3x3 matrix. And this is a tensor-free matrix. And we say the pressure term here, P, is this I to this rho to this gamma times. So as usual, we say this gamma is bigger than 1. But for I just mentioned one more thing is that for the existence results, we have this gamma is up to this 3/2, and we can I barely see anything that's less than this number. And this L stands for the lemma operator. L is the so the operator is for the viscosity, and this is the operator it shows. So the numbers known as lambda, that they are positive and they are viscosity coefficients of this fluid. So the next will be some other notations in this equation, like this term gradient at Q or times with gradient at Q. It's also a 3x3 matrix, and its every component is defined like this. We say this I3 in the equation is a 3x3 identity matrix. FQ is a free energy density like this. We can see the difficult things in this FQ is about this trace of this Q to this 3 times, and the trace square to this Q to this square. And we denote its HQ like this. We separate it into 2 parts. It's this total this L Laplacian Q and the kappa Q. And the theta will be the skew symmetrical part of the strand tensor. It's defined like this. So in this paper, we are just focused on the equation just added with the multiplicative noise. We can see we have added this G to this rho to this rho U dW here in the momentum equation. And we said this W is the cylindrical window process. And the initial data is defined as this ρ0, U0, and Q0. So just one thing is that since we have defined this ρ0 to be positive, that's away from the vacuum state, we can define this initial condition as this U0 solely instead of the initial momentum, this ρ0, U0. And we also say this Q0 is in the trace-free space. And for the variable x, we just consider the periodic boundary case. And each period is a cube and defined like this. So for the stochastic setting, we just added this background that's stochastic basis, omega f, ft, p to this w. And the w is the window process, and it's adapted to the filtration ft. Also, we said this window process can be decomposed into a sequence of independent one-dimensional Brownian motions with this EK to be the complex orthonormal basis of U. And another notation is that for the auxiliary space U0, defined like this, just with respect to the basis for the Hilbert space U, with this norm defined, and also the separable Hilbert space X, the definition for this L total is Ux and its norm, also corresponding to the basis EK. So here are some of the previous results in this field. We set the model for the deterministic model for the Q tensor. This model had been brought up in this paper, this Barris Edwards paper, and before that, we use the model of unit vector D to describe the motion of biaxial liquid crystals. And I would say that the model of Q tensor reflects better the properties of nematic liquid crystals. And we said the coupling of the Q tensor equation and with this Navier-Stokes equation describes the flow velocity in a liquid crystal. And also the deterministic liquid crystal model has been studied by all these papers. Also, there are some results for the stochastic nematic liquid crystal model, mainly the incompressible model, that's involving the unit vector D as I have mentioned. So you can see the results in these two papers. And also, me and Xiu has obtained the global existence of the weak martingale solutions to the compressible active liquid crystal system. So I would say the active liquid crystal system is just very similar to what we are doing here. It's just we have added another active term there. And I would say this results for this paper can be extended to the active system as well. And the last thing is that I have just obtained the incompressible limit of the compressible liquid crystal model. And you can see the results in this paper. So we start from the definition of the whole paper. So the definition of the local strong pathwise solution. So here the local means the solution exists locally just up to a stopping time. The strong means the solution is strong in the PD sense. And we said the pathwise is just similar to what we said, the uniqueness, and we will define this later. So we say a local strong pathwise solution includes this rho UQ and the stopping time. With this stopping time, first is the strictly positive, almost surely FT stopping. Also, this rho UQ are FT progressively measurable, and it satisfies all these equations, all these conditions, I would say, and up to the stopping time we are given. Also, we say for the t, for any time that's in this 0 to t, we said the equation is satisfied. It is satisfied up to the stopping time. That's taking the minimum of the t and this stopping time. So for the pathwise uniqueness, we say if we are given two local strong pathwise solutions, ρ1 U1 Q1 T1, and ρ2 Q2 U2 Q2 T2, and if the initial conditions that are equal almost surely, we say these two solutions that are equal almost surely up to the minimum of 2 stopping times. And if we are given a set of local strong pathwise solutions, we can build up a maximal strong pathwise solution. So maximal pathwise solution you can see is here rho UQ, a set of stopping times tau n. So each set is a local pathwise strong solution, and tau n is increasing sequence of stopping times, with every tau n is defined like this. So the norm total is infinity, and 3 to this infinity norm, that there are the subloop spaces, W total is infinity and W3 to this infinity. And we say the limit of this tau n is the maximal, is the maximal stopping time it can exist. So our main result is like this. So if we are given the condition for the G, the random perturbation coefficient is like this. So it's bounded, and this one is for the contraction. So assuming that for any S that's bigger than 902, So, and the initial data Rho0, U0, Q0, F0 measurable random variable, and its values in this WS2, WS2, and WS plus 1, 2. So this S03 is the space for Q0, that's the trace-free matrix. Also, we said this Rho0 is away from vacuum almost surely, so there exists a unique maximal strong pathwise solution, Rho-UQT, to our system. And the idea of this proof is inspired by this paper. So since we have assumed the vacuum state does not appear, we want to write our system just as a symmetric system. That is like we said in the Navier-Stokes equation, there is a term that's rho to this u dot with gradient u, and we want this 1 over rho to we want this gradient rho to this gamma times is just similar like this. So we write this 1 over gradient x rho to this gamma times into this form. And if we denote this r as a constant, some constant times rho to this gamma minus 1 over 2, this one becomes this r dot with gradient xr. And we also denote this dr as 1 over rho, and f is as this 1 over rho times d. So I think at the last talk I also talk about this. The nonlinear terms in these equations are hard to estimate, so we add the cutoff function to the nonlinear terms, like percent r to this uq. So this cutoff function equals to 1 when the total is infinite norm, as well as the 3 infinite norm of q is less or equal than capital R, and it's 0 if this total is infinite norm and 3 to the infinite norm is bigger than r plus 1. And we write it as the symmetric form like this. And for the existence of such a strong solution, we use also the Gluco approximation. So first of all, it's like just think from here. If we are given that u to this total is infinite norm is bounded, this u is bounded, and divergence xu is bounded by capital R. So by using the transport equation theory, we say this R is bounded both from up and below, and these bounds are dependent on this capital R, given that the initial value for this R is bounded. Also, the gradient xr is bounded, also the value is dependent on the capital R. And for the existence of Q tensor, we said that for a given u here, then there if for a given u that's in C to the 0t xn is a finite dimensional space, and any integral s bigger than 7 over 2, there exists a unique solution Q that is in C to the 0t, ws plus 1 to this 2, and ws L2 to this ws plus 2 to this 2, given the initial condition, initial value problem like this. And also, if the initial value is smooth enough, this mapping is continuous on a bounded set. So for the existence of u, we construct the approximate solution to the momentum equation. So this is like we said this percent m is an orthogonal basis for this H1, and set the space Xn is the span from percent 1 to percent n, and Pn is the projection from H1 onto this Xn. So this approximate velocity field Un is a solution to this momentum equation. So we can see this this approximate solution is built just up to the inner product to all the bases in Xn. And the initial condition is projected onto this Xn. So another thing to note is that in the existence of Q, we need the norm for the Un to be we need the norm on X end to be bounded. So we add another cutoff function here, that's percent K. So we define this V like this. So this X norm of U of V is bounded by capital K, and we define this mapping on of U onto itself. It's tau U, and we use this UK. So after proving that this mapping is a contraction, and the contraction is not dependent on capital K, so by passing this K to this infinity, we can see that there exists an approximate solution Rn Un Qn for any fixed n, and for any on the space 0 T for any capital T bigger than 0. So the next thing is that we need to pass this n to this infinity. So by this, we need to get the estimate that's independent by this n. So we take this up all the derivatives on the momentum equation and apply the Ito's formula. We can get these bounds. So we say this stopping time tau m is what we have taken as this as to this two norm of U and S plus 1 to this norm is bounded by capital M. So if we can take this M to this infinity, we can get the bound for this Rn, Un, Qn. That is that these bounds are independent of 1. And for any P that's bigger than or equal to 1, less than infinity, and integral S bigger than 7 over 2. So I would say this S bigger than 7 over 2 is taken just by embedding that we need this we need to embed this subloop space S to this 2 to this 2 to this infinity now. So after getting the uniform estimate, we need to get past this n to this infinity. So here is the difference from the from after using this random variable in the equation than the deterministic case. We cannot just directly take this n to this infinity. We will use this define this path space cosine. That's cosine R, cosine U, cosine Q. Define this correspondingly, and define its corresponding probability measures mu n. And since we have got the uniform estimate with respect to n here, we know that this mu n is weakly compact. And by this square-hole representation theorem, we will be able to prove that first there exists a new sequence Rn tilde, Un tilde, Qn tilde, W tilde, equipped with also a new probability space. And this new space has the same joint law as this odd one. And the new space is weakly convergent to this R tilde, U tilde, Q tilde, and W tilde. So we have found the limit, and it remains for us to just verify this R tilde, U tilde, Q tilde, W tilde is a solution to our equation. So that is to prove the following theorem. So here, if we say this R0, U0, Q0, just also bounded in this LP, this WS2, WS2, WS plus 1 to 2. And we have just assumed in addition that Q0, R0 are bounded by capital R. So we know that there exists a strong martingale solution to the system and equipped with this initial law. And we also have this R to be away from, also R is bigger than some number that's bigger than 0. And that's R to this RUQ that are bounded. So the next thing is to prove the pathwise property. So this is just the same as this proving the uniqueness of the solution. That is the following theorem. Just assuming this R0, U0, Q0 same as before. And we have for any integral S bigger than 9 over 2, this system has a unique global strong pathwise solution. So first we said that to prove this uniqueness, the regularity had to be higher. That's from s bigger than 7 auto to this s bigger than 9 auto. And also, since we have proven this uniqueness, we can just recover the existence of the solution to the original probability space. And the method is used, and we use the method that can be seen in this paper. So finally, that's our proof for the main theorem. So just first to summarize, we have proven the existence of a strong pathwise solution, and under this assumption, all the initial conditions that are bounded. And this capital R is chosen according to M, though this capital R is chosen just by the embedding from this subgroup space S2 to this infinity norm. And we will be able to drop this auxiliary boundedness on the initial data. Just use the idea in this paper. And then we prove this RUQ had a continuous trajectory in this space almost surely. And since we have proven this R to be positive, so after transformation, we can just recover this RUQ back to this rho UQ, and with this rho 0 to be positive. So here we have established the existence of a local strong pathwise solution, rho UQ, to our system just by our definition up to a stopping time tau. And finally, just by this constructing all this stopping time tau, we will be able to extend the existence of the solution to maximal, just follow the ideas of these two papers. So our proof will be complete here. And here are some of the references we have used. And thank you for listening. Have you got any questions?
I actually have a question.
Yeah.
Oh wait, I'll stop recording before that.